Hello everyone. We are excited to present our work on potential field as scene affordance for behavior change-based visual risk object identification. Intelligent driving systems attract significant attention in academia and industry, aiming to provide immediate alerts to help reduce the number of road accidents. One of the indispensable technologies is visual risk object identification, which involves localizing potential hazards and estimating the corresponding risk scores. Our study explores the challenges involved in applying causal inference to identify risk objects within the framework of behavior change-based prediction. In this paradigm, risk objects are defined as objects that influence driver behavior or ego-vehicle behavior. Existing methods often show significant limitations in spatial accuracy and temporal consistency. Specifically, existing methods often misidentify vehicles that do not affect the ego-vehicle's behavior as risk objects, such as vehicles in the opposite lane, resulting in numerous false alarms. The root cause of these misidentifications lies in the model's lack of understanding of scene affordance. In other words, what actions does a given scene afford an agent? For instance, in this case, existing methods can identify that there is a vehicle, but they fail to recognize that it is positioned behind the opposite lane. These methods face another challenge. The process of performing causal inference with perspective view images is time-consuming. Since they rely on vision-based approaches, the entire causal inference process involves multiple steps, removing objects, inpainting images, and extracting features. These steps render the method impractical for real-world applications, especially in real-time systems, such as autonomous driving systems, where speed and accuracy are crucial. Based on the two challenges mentioned above, the key questions are: how can we reduce false alarms, and how can we improve the efficiency of causal inference? Our insights lead us to this solution, representing scene affordance in a bird's-eye view space. What is scene affordance? In the context of traffic scenarios, scene affordance can be understood as environmental features that assist drivers in making decisions. In everyday life, typical examples include traffic diversion and opposite lane. In our research, we introduce the repulsive and attractive forces in a potential field as representations of scene affordance. Repulsive forces informs an agent to avoid obstacles, and attractive forces guide an agent toward a goal location. Here is an overview of our framework. This framework is divided into 4 key components: 1 BEV segmentation, 2 target point prediction, 3 potential field rendering, and 4 behavior change prediction. In contrast to previous works, our proposed method performs causal inference in bird's-eye view, enabling parallel object removal and using potential fields as a new representation of scene affordance. This approach provides richer information for reasoning about risky objects. We used RiskBench to evaluate our model. We demonstrate that our proposed method PF plus BCP achieves state-of-the-art performance compared to existing Visual-ROI methods. Our methods show a significant effectiveness, delivering a 20% improvement in the F1 score over BCP. Furthermore, we observe a 2.6% improvement in the F1 score compared to BS plus BCP, emphasizing the advantage of integrating attractive and repulsive forces into the model. In terms of temporal consistency, PF plus BCP shows an improvement in WM/OTA of 11.6% compared to BCP and 2.3% compared to BS plus BCP. The improvements in PIC further validate that the proposed method enhances both spatial accuracy and temporal consistency over existing models. Moreover, we demonstrate that employing BEV representations for causal inference significantly enhances inference speed, achieving an 88% improvement compared to BCP, which uses perspective images. This chart provides a visual comparison of the performance across different Visual-ROI methods. Each point size represents the normalized PIC score, with larger circles indicating better results. It is clear to show that our method PF plus BCP achieves higher scores across all key metrics. We also analyzed the 60 frames leading up to the critical frame across all scenarios. As shown in the figure, performance for all methods improves as we approach the critical frame. Notably, PF plus BCP, represented by the red line, consistently outperforms the other methods throughout most of the timeline. We perform a scenario-based analysis to assess model performance across various traffic conditions. PF plus BCP demonstrates fewer false positives compared to all baselines in the opposite lane scenario. This strong performance is due to its focus on objects that may influence the ego vehicle's progress toward its target point of attractive force. Moreover, the modeling of repulsive force helps identify non-afforded actions toward objects in the opposite lane. PF plus BCP significantly outperforms other methods in scenarios involving the various actors, as shown in right table. These demos show the visualizations of ROI results on sample scenarios from the RiskBench dataset. We conducted extensive ablation studies to validate our design decisions. When we combine all the designed modules, as shown in ID 5, we achieve the best results, with a 20% improvement over the BCP. We use the NewScenes dataset as the testbed to evaluate the effectiveness of different Visual-ROI in the real world. However, NewScenes dataset does not have the annotations of risk objects. We label risk objects manually according to the protocol described in BCP. As shown in table, PF plus BCP outperforms the baselines BP, BCP and BS plus BCP in both spatial accuracy and temporal consistency metrics. Notably, both BS plus BCP and PF plus BCP exhibit substantially inferior performance compared to BCP in terms of OTP. We conjecture that this decline in performance stems from the limitations of BEV-SEG predictions, particularly in complex real-world scenarios. Let's take a look at failure cases. In the first example in RiskBench, the pedestrian was too small for the perception model to detect, leading to a missed recognition. In the second example in NewScenes, the absence of road lines at the intersection caused the model to generate a false positive due to the lack of clear road affordance. We have developed a user-friendly interface for scenario-based ROI analysis. For further exploration, please visit our project page. Thank you for your time and attention.